Okay, we are recording as of now. So hello, good afternoon, everybody. I'm very happy to welcome you in the new room. Well, the room is empty because of the pandemic lockdown in the academia in Warsaw, at least. We are no longer allowed to teach in class. We are fully online. But this gives me an opportunity to test some brand new equipment. So please be patient, please be indulgent. If anything goes wrong, bear in mind that we are doing it for the first time. And actually, it's the first lecture ever at this super duper 5,000 euro digital whiteboard or blackboard. Yeah, actually it's a whiteboard because I'm using Zoom. So yeah, it's going to be fun after more than a semester of lecturing while you sit down and write like on a piece of paper, but I actually write with something which is a digital chalk on a digital blackboard. Let's see how it works. Unfortunately, for starters, I have to remind you where we stopped last time. This is the disadvantage of breaking a proof. I remember in the first semester of this lecture course, about a year ago, I had a very long proof and I did it in one go, but my lecture was full 3 hours. So on one hand side, this is inhuman to listen for 3 hours to precise argument. But on the other hand, I didn't have to recall anything next week. I was done. I started the proof at a given hour and I ended it 3 hours later. This time our proof was broken in the middle, more or less. So I have to remind you a notation, right? I have to remind you the formulas which I'm going to compute with. So for starters, please remember the definition. Can you see my handwriting? Can you see what I'm writing?
Yes, yes.
Okay. How do you construct this graph EX? I know we did it, but just to focus attention and to fix the notation. So EX, of course, is a graph. So you have EX 0, EX1, S, EX, and TEX. And what is very important is that X is a subset in the set of regular vertices of the graph E. Y is defined as the complement of X in the regular vertices. Now we define F to be, and then we have this Y prime, remember, Y prime is a disjoint copy, yes? So Y prime disjoint copy. And now what is important is that we have F, and this will be helpful when writing formulas. It will be shorter. So these are all edges in E1 with the property that they end in Y. And then I take F prime to be a disjoint copy of F. Okay, and now I'm ready to define, to remind you, I mean, we did it, but we have to have this notation, a random access memory. So EX naught is by definition E naught union Y prime. And that's a disjoint union. I can also write it like this, but by construction they do not intersect. And likewise, EX1 is just E1 set union with F prime. And again, this is a disjoint union. So this is E1 disjoint union F prime. This is why for all our formulas, we just have to say what happens to E0, Y prime, E1, F1. And I apologize for not being able to distinguish between my 1 and my prime. Okay, so that's the first definition that we have to bear in mind. Now, how do I go to the next page? Oops, right here. And I also need this formula for psi inverse. We need both formulas, but the formula for psi inverse is more urgent, and I have to recall it. And, let's see if it's more convenient to type on such a blackboard than on the tablet. I will try to use smaller fonts so that everything fits. And have zillions of cases, as you remember. So that's the class of QB for class, okay, for P being equal to V prime and V in Y. So I can write P in V prime, but that's more comprehensive. Okay, it is chi P minus QP. Sorry, QP. Or simply P in Y. Oh, I'm sorry, this is so convoluted. Let me rewrite it. Q P. For simply P in Y. And we have this lazy part when P is in naught less Y, then this is simply a class of chi P. So nothing happens here. Now the class of, if I now let's look at edges. So it's the class of chi E where E is an appropriate edge times the class of Q dE of E. And yeah, I forgot to write 4. And now this is P is equal to E prime, sorry, equal to E prime, and E is in F. Okay, so like in the first case, I have to write it this way because I'm depriming my P, and then I obtain E, and then I write the formula using E alone, but E must be in F. This is very important. And now if it is just P, which is in F, okay, then the formula is most complicated because it's the class of chi P. And now what we write chi, sorry, I'm still learning how to use this digital chalk. Everything works slightly differently. Suppose, so this is the class of chi T E P minus the class of Q. Yeah, I waited to do this for. Minus the class of Q at the same vertex. So Q at T E of E. Okay, I close the parentheses, and now this is for P in F. And then it's just the class of chi P for P in E1 less F. And now I have to start these 3 formulas, and this time I should be able to fit it in. So I have, and when I start, I have to flip the order. So I will have a class of Q T E E times the class of chi P star. And this is for P equal to E prime star. So as complicated as it gets, okay, with E being in F. And now I flip this formula. So I have parentheses, the class of chi t e of e minus the class at the same vertex of q at the same vertex of q t e of e. And now comes the star part. So this is chi of e star, I mean the class of e star. And this is simply for p being equal to e star and e in f. Yeah, sometimes when I don't take my hand sufficiently far away from the blackboard, it makes such a smudge. Okay, so this is for e, of course, in f. And the last one is the lazy part. That's just chi of e star. The class for chi of e star for p equal to e star and e not in f. So e1 less f. Okay, wow, and that's already one big advantage. I fit the whole formula on one page, and I think that my handwriting is more legible because what I write is much bigger. This is quite. And now what we remember, we have to check that this psi inverse, so it's not as good as I wish it to be, but we are trying in our learning. Draw psi inverse. Okay, and now we have to show that it's well defined. And much as before, only one formula is really interesting, the condition number 5. I already wrote for you conditions before. I'm not going to write them again. The condition number 5 that we are to verify, it says what happens for the regular vertices. So I have a regular vertex. I have my second type conjugate relation, and I want to check that this is preserved. And believe it or not, this is just a calculation. It's a lengthy calculation, and I need this formula to make sense out of it. And it's not so completely boring. All other checks of conditions 1 through 4 are much easier, and we'll still do some of them. But the most important one is this second conjugate relation. And remember, this is the domain of psi inverse. So we are talking about the Levitt path algebra of the graph EX. Okay, so at every regular vertex we have a conjugate relation. All right. So for all v in the set of regular vertices of EX. But here we are lucky. Remember, we discussed it as one of elementary facts. We know that regular vertices of EX are the same as regular vertices of X. Of E, sorry, of E. Well, basically, you know it because the vertices that you add are in Y prime and they're all 6. So they cannot be regular. So now it's very nice because we are just looking at regular vertices at E. And we just compute. So I take psi inverse of the sum, and I take all just E emitted at this regular vertex. So E belongs to the preimage under SEX of my vertex. Okay. And now, of course, I have this chi, the class of chi E, times the class of chi E star. And as you know, we want to just get psi of chi of the end of E, all right? Psi inverse of chi of the end of E. But let's just compute it step by step. So the first step is very simple. I just use the fact that psi inverse is defined as a universal map because we look at the length of algebras given by generators and relations. So it is by construction and algebra homomorphism. So I pass it through the sum, I pass it through multiplication. So I end up with the sum, and here some fun will begin. But let me write it first. Yeah, if you don't take away your hand sufficiently far away from the board, you are smudging. Okay, so S, E, X, preimage of V. And now I'll put psi inverse of chi E, psi inverse of chi E star. Okay, but without rewriting, let me split it into the following cases. Actually, to be consistent with my notation, I know that this is just notation, but otherwise I might get myself confused. I used, for whatever reason, I use an H here. Because I want to end up with E. So here, for these dummy indices, they're just for the sum. I use H to denote an edge. What is important is V. V is fixed. Okay. Although arbitrary. Okay, you have the same sum, and here you have chi H and chi H star. All right, but remember that this is in the graph X, okay? So we have like three subsets in E1X. One is E1 without F, one is F, and one is F prime. And what I'm going to do, I'm going to intersect this preimage with these three subsets. I just write my E1, oops, this is dangerous, one shouldn't do it. I touched something and my whiteboard shrinked. Okay. So maybe I'll write it here. This is dangerous to use this portion. I remember that E1X is in fact the disjoint union of E1 plus F, F, and F prime. Okay? So because I view this SEX as a map from E1X into E0X, that's where this is what this is a subset of. Okay, but now I intersect this subset with this decomposition, and now this sum will split into three independent sums. Okay, so first I intersect with the easiest part, which is E1 without F. Okay, then plus, and I will not repeat this is the same what I sum here, but now I have a sum with H running as the preimage under SEX of V. This time I intersected with F. And finally, I have a sum over H running the preimage under SEX of V, but intersected with F prime. And you can immediately guess why I am doing this, because it depends on where the H is, what formula I apply for psi inverse. Okay. All right. So for starters, when we are in this easy part, nothing changes, right? Remember that when you have an edge which is beyond F, which is in E1 and beyond F, then with psi inverse and psi are just tautological guys. All right. So I can simply erase this psi inverse with the understanding that now these are the equivalence classes in the relative concave algebra. Okay. But that's it. As long as your H is in here, this is what happens to, this is the formula for psi inverse applied to these guys. Okay. And now, if you are in a situation in which you intersect with F, okay, so let me go back and remind you this formula. So that's this one, okay? Why isn't it writing? All right, P is in F. So if I have to write this complicated formula over here, and it's analog for the star. Okay, so this will be quite lengthy, but I should be able to fit it. Okay, so what do? We clean some space. It's so nice there's no dust when I erase this digital chalk. And in fact, let me start this sum over here. So it's H running the preimage under Sx of V intersected with F. Okay, so now I erase this here. And apply the formula. And this formula spits out the following. This is a class. Oh yeah, and this is why I changed the notation from. Wait a second. Maybe this is pointless. I will keep this H. I'll just keep it. All right. So I have the class of chi H times in parentheses the class of chi of T of H. But it should be actually TE of H. Right, because this is psi inverse, and we already applied this formula for psi inverse. So we are in the relative concave algebra, so we have only the graph E. Okay, so here is EX, and here is E. Yes. So all right, I should have done, yes. So this is, sorry, so there was some wisdom into changing this notation, because by applying this psi inverse, of course, that's the same edge, but now I cannot write SEX anymore, because now I want my H's to be in the graph E. So this is why I changed the notation. And this is why I put here okay, this is just a dummy variable, it's a sum, but it introduces some tidiness in the formula. So now these are E's running the set. So the most important thing is that I erase X here, okay? And now I put E and E star. That's just notation, okay? That's just notation. This is the result of applying psi inverse. The set is exactly the same, but we should remember that E is a subgraph of EX. And now we are doing it in this subgraph, so let's change the notation to make sure that we remember that we are now in the graph E, not in the graph EX. Okay, so this is why here I changed into lowercase f. So this is chi f, this is chi of TE of f, minus the class of Q of TE of f. So this is the result of psi inverse applied to the first term. And now we have a second term, which should remember involves star. So this means that we first write this parenthesis. Okay, so this basically it doesn't change. It's the same parenthesis because if you want, these elements are self-adjoint. So whether I'm in the star part or non-star part, they are not changed. I just change the order. You see? If you look at this penultimate row, the spot in the parenthesis is not star. There's no star. You have only star when you after the parenthesis in this chi e, you have chi e star. Okay, that's why I can simply write this expression squared in order to save space. So this expression in parentheses, which is sort of self-adjoint, I mean self-adjoint to B once we go into star algebras, it's sandwiched between chi e and chi e star. So this will be very convenient not to write it again. I'll just square it. And then I simply have to write the class of chi f star. All right? And now have the third sum. Again, I'll push it to the left. So I now use the notation, what notation do I use? Well, yeah, there was some wisdom to this notation because now I again use the notation for f because remember there is no such a thing as f prime, okay? And we basically, when we had this formula with still psi inverse being around, so maybe it wasn't a good idea to erase it because now I cannot go back to it. But okay, but you still have it here. So I have psi inverse applied to this class of psi h times psi inverse applied to the class of chi h star. And now, if you are in this prime part, okay, so the third summand, remember that what this formula tells you, it tells you to deprime your edge, okay? So this edge will run the same set. It will as in the case when it is not prime. That's just by this formula for psi inverse, okay? If my P is in F, but not in F prime, I have a certain formula, everything happens in the subgraph. But now I am beyond the subgraph E, I'm really in EX. I'm talking about something which is in F prime, okay? So that's this formula. Now I'm talking this formula. So let me erase the old part. So I'm now talking P in equal to E prime and it's adjoint. So this is where this is here. Okay. So these are these two formulas that I'm using, and see how it works. When I'm in this prime part, I'm depriming P, and I'm taking E, which is in F. That's why the third sum now runs exactly the same set. Of course, we know that there is a bijection between these sets because there is a bijection between F prime and F by construction. So here I repeat the same F, and I'm running over the same set. So this is pre-image under SE of V intersected with F. That's precisely because in the third summand, I'm simply depriming to make sense of the formulas in the subgraph. Okay, but now this formula will also change because, but it will change only in this respect, that here, instead of this difference squared, I will simply have QTF squared. Let's double check. Yes, this is just QTE and QTE. And now we'll be sandwiched between chi-E and chi-E star. Or in my notation here, the class of chi-F, the class of Q TE of F squared. Let me erase what I already moved to the left. And the class of chi-F star. Okay. So wow, so that's the first step, and I saved a bit of time by erasing psi inverses and not rewriting everything. But here you see the magic happens in what you sum over, all right? And now we just have two different sets for the summation. However, you still have three sums. Only right now you are scaling different summands for F in the first place and then in the second place. And now we are using a lemma which we proved, I believe, at the beginning of a lecture a week ago. Namely, we proved that this is an idempotent, and that this guy in parentheses is an idempotent. We proved it. Okay, so I might just erase the squares. You cannot stop me from erasing the squares because these guys are idempotent. Okay, so it's already getting much simpler. All right, but we still have to compute. That's not the end of the day. I will need the next page to carry out this computation. Or maybe I can do it by erasing. Let's see. Well, as you can guess, the first summand is already done. We cannot simplify it anymore. Okay, and now when I look, I just have to compute these things over there, all right? In the second and the third sum of what we are. But again, I believe that that's something already done in another lemma. We said that Q, how was it? No, this is in a different order. Let me double check. Yes, so you get a 0, but only when you have unstart on the right and start on the left. That's the other way around. Okay, so you don't get a 0, which is very good. Okay, but we still should compute it. Well, when it comes to multiplying out these guys, that's immediate, right? Because chi TEF times chi F by the path algebraic relation is of course chi F, right? And then when you multiply it by chi F star, again it works because the beginning of F star is the end of F, so it will be all absorbed. Okay, so when you multiply out the first term, you will simply get chi F star. And then, lo and behold, the other thing we don't have to compute because this will cancel out. You see, here I have chi F minus that class of Q TEF chi F star, and here I have chi F Q of TEF chi F star. So simply, I can say that this term and that term cancel out. And I can do it because I sum over the same set, right? So now things really simplify. And I can write it as this sum plus that sum. So the first one was over E, running the preimage of V under SE, but intersected with E1 minus F. And here just have the class of chi E times the class of chi E star. So what is now the second summand? Well, now it's about the complement of the sets in E1. So this is just, oh, sorry, I'm using F here. So it's the sum over all F, which are in the preimage of V under SE, but intersected with F. And let's double check what we've got there. And this will be, okay, maybe I'll write it down and, well, no, I mean, this class of chi TF is absorbed, I will explain. So I'll write just the class of chi F, the class of chi F star. All right, but now, if you look at these two sums, they're just the sum over all G's running the preimage of V under SE, right? So I can bundle it up into one sum. Now let me call it G, it's a dummy variable anyway. But now I no longer divide this set into two disjoint subsets. It's just the preimage of V under SE. That's it. And here I have the class of chi G times the class of chi G star. All right, and now we have to remember where we are. This V is, of course, a regular vertex in E, okay? And we are now in the relative compact algebra. So this is now important to see whether we have a Kunstfigure relation here or not. And this means that, let me see. Because I want to write it down, you know, as psi of chi, sorry, as chi TG, right? But I have to make sure that I'm in the right vertex. Because this is no longer in the left part algebra, that's it. You have everywhere, every regular vertex, you have a second Kunstfigure relation and you can fold it up into the final projection. But here, I have to somehow justify it. Please bear with me. Okay. Haha, okay. So that's, yes. That's something beautiful. That's something very subtle. It's really good to have notes. Let me first write it down and then explain. I claim that this is equal to class of chi V minus the class of QV. And now let me justify. Look at this formula for psi inverse and look. So now let me raise these arrows. Okay, and I'm looking for these two formulas. All right. My V is a no, sorry. I'm looking actually at these two formulas. Second and the third one. Okay, so if here I would, instead of E0, I would have the regular vertices in E, then I wouldn't have to change the formula, because remember that if you replace E0 with regular vertices, then you end up with in X, and then things vanish or don't vanish. So if you want here in this general setting, I have to write it down like this, because I cannot make sense out of QP for an arbitrary vertex in E0. If vertex P is not regular, then the definition of QP doesn't make sense. Okay, but here I assume. Remember, this was our assumption when we started the calculation. We assume that V is a regular vertex, so the definition of QV makes sense. Okay, and now you just have to observe is where we implement the Kunz trigger relations. Now I forgot to implement them at, at X or at Y. Can somebody remind me? Okay, so we'll figure it out. Yes, of course. When P is in Y, we implement them at X, not at Y. Then this QP is something different from KP. Otherwise, I would just write 0 here. All right. But if P is irregular, then this sum basically splits into P in Y or P into regular less Y. Right. But regular less Y is simply an X. Okay. And an X, we implement the Kunz trigger relation, and this is precisely where QP vanishes. QP is 0 for every P which is in X. All right. So when I write this formula in one go, I have both cases. When V is in X, then this is just chi V, and when V is in Y, this is chi V minus QV. All right, but it's convenient because I don't have to write cases anymore. This is a very neat way of writing it down, so I can finish it by writing that this is psi inverse applied to the class of chi V, which is precisely what I'm supposed to verify, okay? Because the relation number 5 was simply saying that all this left-hand side here has to be equal to psi inverse. And again, I forgot that I shouldn't write close to the top. This is so annoying. Zoom has some ugly quirks. It just shouldn't be there. Okay. Yeah, I want it to be psi inverse of the class of chi V. Right? Because the domain of psi inverse is the Levi-Taff algebra. So we have Kunz trigger relations at every regular vertex. Okay, so that sum is just equal to the class of chi V. And this is exactly what we were supposed to verify to prove that the relation number 5 is preserved by psi inverse. But now, of course, we have to split. We have to write down this set of regular vertices of E as X disjoint union Y. All right. And so V can be in X or it can be in Y. And now when we look at the formula over here, right? Then this is consistent. Then this is consistent because if P is in X, then I can write chi P minus the class of QP, because QP is 0 when P is in regular minus Y. All right. So that's why I don't have to write the cases, and this is my formula. Yeah, I have to write the cases because P can be beyond regular vertices. So this proved it. Okay, done. We checked the most interesting relation, and I think that this is nice. Okay, I maybe should write it down. So here, the last equality holds because the class of QP is 0 for P in X. Okay. All right, so we still have the other 4 properties to verify. I'm definitely not going to do 3 and 4, but let's still do 1 and 2. Okay, so 1 and 2 should be very simple. Let's see how it works. This is, I didn't write it in the lecture notes because this is straightforward and awkward to write down because we have 4 cases to consider, right? So I will not now write it formally. I will now skip this baroque notation. This calculation was sufficiently interesting to do it slowly and formally, and I think this was a pretty nice calculation. But now these are just some tedious verifications. I still want to run through 2 of them, but I will now do it in a sort of informal manner as we did before. So I have the W, and I have 2 cases. I can be in E0, or I can be in Y prime. So these are just 4 cases I have to consider. And what we have some nice, would be nice to have some notation. I don't know, maybe X. I still keep on forgetting to write in a slightly different manner than on a tablet. X, Y, and I don't know, P, Q. Okay, so D is X or Y and W is P or Q, and this is just re-understanding where we belong. Right? Okay, and of course, what we have to compute is sine inverse of chi V, chi W. I was supposed not to write it. Okay. Okay, I'll stop from now on. So let's do it case by case. So now let's see what happens with X and P. So we are in E0. What does sine inverse tell us to do? Well, in fact, yes. In fact, we have to split it further. I'm afraid. So this is X, Y, Z. Okay, how do I do it so that I'm consistent? And PQR. So to be consistent with how I define sine inverse. Okay, first I do Y prime, then I do Y, and then beyond Y. Okay, so this is in Y prime, this is in Y, and this is in E0. less y. So I'm trying here to 9 cases to verify. That's why it's really useful to skip the notation. Now, when we are in the case when we do xp, so that's this case. We are unpriming our guys and just writing qv as this vertex. Okay. So yeah, so actually it will be useful to write it as x prime and p prime. And basically the result is that this is q x times qp. I skip writing classes and everything, okay? But remember, we had this lemma, which told us that this is precisely delta xp qx. And then it agrees with what we want to have, okay? Because on the other side, we will have, and I'm just using the fact that this is the same as Kroneker's delta between x prime and p prime, okay? And now the result agrees, because the relation, okay, maybe I should finish the relation we are checking. So this should be sine inverse of Kroneker's delta between v and w, the class of qv. Yes, except that I should still prime it. Wait a second, no. I'm writing some notes. Sorry. Where? This is prime right. This is w prime right. But here, of course, I just have chi v prime, not q, right? And sine inverse applied to chi v prime is just unpriming v prime into v and writing q at this right. So this is precisely what happens here. And the Kroneker of delta xp is the same as x prime p prime. So check, the first case is done. Now I'm taking, say, x prime and q. So for x prime, I'll have qx. And what do I have for q? So now q is in y. And when we are in y, we apply this formula. So here I don't have to prime anything, but I just write the difference. So I multiply by q minus qq. Yeah, let me double check. Yes, minus qp. Okay. All right, so qx q will give me just the Kroneker's delta, and now if you remember the definition of qx, for this to make sense, I have to know that x is the beginning of q. Otherwise this is 0. Okay. So we want to get Kroneker's delta. let's see, y is okay. Let's see. This is not so completely obvious. I have to compute qx times q, and here I have just Kronecker delta. That's easy. Delta xp q x. Okay, I have no choice. I have to recall what this is, and so qx is just defined as x minus sum of some edges running with the image of x, and here have e star. And I multiply by q. All right, so I guess here the argument should be the following. So we want, okay, so if I should remember that q and x are, oh, okay, q is just a vertex. Q is just a vertex. So of course, remember that the end of E star is the beginning of E, but the beginning of E is just X. So if Q is not equal to X, this will vanish. Okay, so this is important. And if Q is equal to X, it will be absorbed by X and by E star. All right. So this is also well, I can now write it down simply by erasing. This Q either gives me 0 or is absorbed. Okay. So this will give me the same formula, so it will be 0. Maybe I will erase at least this part. And delta xp. And well, q x. I'm confused. It shouldn't be 0. Unless it's 0 over there. Oh yes, of course. Remember that all these cross terms have to vanish because obviously x prime and q are in disjoint sets, so they are different vertices, so they do multiply to 0. So this should be 0. Okay. Oof, I'm sorry. But you see, it's not so completely stupid to do it because it's, I know it's trivial, but it's not entirely obvious. You have to somehow see this machinery working. And now again, this should vanish because this is a cross term. And okay, so let's write it down. I have q hooks, but I have to switch it into my chop. I have qx as before. And now what happens at the regular vertex? That's easy. Nothing happens. No, not sorry, I shouldn't say regular. What happens at this lazy vertex, a vertex which is not in y? It's in E0 and not in y. Well, then remember, the formula tells you that you should do nothing to it. So this is just times r. But we already argued that when we multiply q at a vertex by a vertex, we have Kronecker delta. So this is Kronecker's delta of Rx, Qx, but since this is, they are always different, that's 0. Okay. All right, now why P prime? Why P prime? So when I have to remember, okay, so for P prime, I will just do P. And again, we should get a 0, right? Because these are definitely different vertices. Okay, and what do I have if y is in y? I have to go back and check. Okay, then this is y minus qy. It vanishes for the same reason as here. That's exactly the same argument. That's exactly the same calculation. Okay, it will vanish. And in fact, here I had to have this difference. You see, because it might be that when I do the unpriming, that they end up being the same vertices. So here it's good that I actually have a difference. This on itself does not vanish, right? Okay, but yes, here I have y and p prime. So y and p can be the same. They can be the same. Luckily, here is the difference, and in both cases you'll get Kroneker's delta between y and p, and q with y or p, whatever. So that's still 0, completely analogously as before. But I emphasize that in general, this is not 0. In general, might be 0, but in general it's not. Okay, yq. So here we'll have a multiplication of the following sort. We will have y minus q y times q minus q q. Okay, so again, as already argued, we get Kroneker's delta everywhere between y and q. The only thing we didn't argue is y times q is Kroneker's delta. Well, again, if you just look into the definition of what's of qq, you will see that y must be equal to q, otherwise it will q completely. Okay, that's totally analogous, because when you write an expression like E star, the end of this expression is the beginning of E, and the beginning of this expression is also the beginning of E. So whichever way you multiply, you must have this y equal to q when you multiply y times q. So the sign is irrelevant. So you have this global Kroneker's delta, and you will have what? You will have just y with a plus, and then you'll have qy 3 times, okay? Once with a plus and twice with a minus. So obviously you just stay with 1 with a minus. And this is good. This is exactly what we should have, because this is the formula applied to y, which is in y, and Kroneker's delta is outside. Okay, so this checks out. Now y and r. Y and r is easy. Just the other. Okay, let me write it down. This is just y minus q y times r. But now, because r cannot be equal to y, this is just 0 as it should be. Okay, the last 3 cases, z and p prime. Now z will just stand outside because nothing happens. Psi inverse to z does nothing. And now this will be times qp, because I prime my p. So it's times qp. But p is in y and z is not in y, so this is immediately 0, as it should be. And now in the second case, well, we have z, and now the difference is that you write q minus qq, but again it's 0 because z cannot be equal to q, so that's immediate. Okay, and the last one is completely trivial because z is mapped to z and r is mapped to r, so of course this will be just the Kroneker's delta between z and r. So that's checked. Okay, this is condition number 1 checked. And now it's kind of boring. I definitely want to skip 3 and 4, but I'm no. Let's do at least half of number 2. There is one with the ends and one with the beginnings. So one with the ends, let me skip. Because it's easier and it's analogous to what we're verifying for the well-definedness of psi itself. So let me just verify this equation. Sine inverse of, I'm still not so good at writing here, but that's my first time. Sine inverse, and okay, I promised you to skip the notation, but at least when I write the first formula, let me be baroque. So I take the class of chi, and now this is, yes, this is the domain of sine inverse, so it's graph Ex. Okay, so it's this huge baroque S Ex of E times chi E. And of course, we want it to be the same as simply psi inverse of chi E. So I'm not going to check the formula when I have chi TEXE on the right hand side. I'm going to do this one. It's more involved because here when you do this division of cases, things get complicated because just because you know that E is in F, you don't know whether it begins at Y or Y prime or wherever. So that's makes life a little bit harder. Okay, and as before, we are going to split. Oops, I should close the parentheses. We're going to split to three cases. Yeah, but here just the three cases because you see, I'm having just one edge. All right. So let me write it as EFG. So I will have, I don't know, E is in F prime. E is F is in F, and G is in E1 less F. Okay, and let's compute it. Let's see what happens there. Now, okay, so maybe the easiest one is the last one, because when G is not in F, then its end is not in 1. And also, of course, it's not in Y prime. So this means that when I look, but I'm still looking, I'm looking where things begin. This is okay. So that part is easier. So let's see what happens with G. Here when G is beyond F, in E1 beyond F, nothing happens. I just have my G. Okay, but the left hand side is a bit more complicated because I don't know where G begins. Okay, I don't know where G begins. I know it cannot begin in Y prime because Y prime consists of 6. But it can begin in Y or it can begin beyond Y. So here I have two options. If this begins beyond Y, then nothing happens. I just write the beginning of G. Okay. But if it begins, so this is for S of G, not in Y. So E naught less Y. So now for SG in Y, it cannot be in Y prime, I repeat, because these are 6. Okay. So what happens? I have to look at the formula of what I do to a vertex which begins at Y. You see, that's the complication which we skipped when verifying the well-definedness of sum. Okay, so this is the second line. This is the second line. So I should write y minus qy. Or g minus qg. Sorry, I should add sg minus q sg times g. Okay, so obviously here this will be just g. And here, what will I have? Well, of course, I'll still have a g, but I'll have this strange sum. Okay, I should now write it down of what this QSG is. So this is SG less the sum over some e's that run the pre-image of the image of G. And here I have E star, and this is multiplied by G. So now look what happens here. So first, these two things cancel because SG is G and that's the opposite sign. So I have only plus the sum. And what have I got here? I have E star G. But remember, E runs a vertex which emits G. Sorry, E runs this. E is an edge which is emitted at the same vertex at which G is emitted. So when you look at the sum, one of these summands, one of these E's must be equal to G because G is in fact in the set. Okay. Of course, the pre-image of the image must include the image. So G is in the set, but only once. And if E is different from G, then by the first called trigger relation, remember this holds regardless of where we are, it holds for any edges, E star G must be 0. So here all terms cancel except when E is equal to G. And when E is equal to G, you have no longer the sum. You just have G star G, but G star G is the end of G, G times the end of G is G. So at the end of the day, whichever case we are taking, we're ending up with G, okay? And this is quite all right, because this is the left-hand side. When G is, sorry, when G is in E1 beyond F, then you should do nothing. And that's exactly the formula. So you see, this wasn't so completely trivial. This is why I wanted to do it. And this is the calculation that we skipped when we were verifying the well-definedness of psi. And even here, when we took sort of this lazy part, it was not so easy, just simply because we have to consider these additional two subcases, all right? Okay, so now how about, so let me now erase it, and let's do F in F. Actually, I don't know why I'm wearing a mask. I'm in an empty room. But I got used to it. Okay, so F in F. Okay, when F is in F, I slowly begin to memorize these formulas. When F is in F, I just write F minus, sorry. I write the end of f times, yeah, I'm not memorizing it. Yes, that's here. No, sorry, this is here. So this is complicated. Yeah, this is complicated. Before I was using formula for the edge, sorry, for the vertex. Now I'm using the formula for the edge. And when I'm in F, this is this most complicated formula, but I'm looking at the ends of this edge. Yeah, so maybe here to be somehow more consistent, we don't mean an E, we mean some H. And now H can be EL by 4G. Okay, so F is in F. And again, we have this problem. If F is in F, it can begin in F or it can begin beyond F. So again, we'll have to consider two cases, all right, for this vertex. We don't know where SE of F is, okay? But I know what happens to what is psi inverse of F itself, okay? This is this complicated formula, which again I have to look up. This is the middle line, so 1, 2, 3, 4, the fifth line. Okay, so this is F minus the difference. F times things minus the, okay, so this will be the end of F minus Q at the end of F. And these are the things that will all be computed. Right? I mean, I still have to write this psi inverse of some stuff. But let us first figure out what this is. Okay, so this will be just F, of course, and now I have minus F QTF. And what happens here? Well, well, it can be what happens here is it 0 or not 0? To be honest, it's not clear to me. Okay, again, I'll have a sum which begins with TF. So this will actually cancel. Okay, so F and F times TF will cancel, and you will have a sum. And here we have F at the beginning. This will be a sum over E, which belong to the preimage of T of F. And here I'll have F, E star. It looks like we have to pay a fee. So here the trouble is that F ends some vertex. So this is T of F, and this is my F. But nobody told you that F is not a loop. So it might happen that it also begins at that. Well, anyway, we look. Okay, sorry, no, sorry. I'm talking nonsense. This is all right because of course E is emitted at TF and F ends at TF. So that part is not 0. This just multiplies. Okay. So I don't see how to simplify it any further. This is what you get from psi inverse applied to the class of chi of f. I don't see how to make it any simpler. So evidently, we now have to look at the other side, okay? So what happens? I look at where the beginning of f might be, and I have to consider two cases: that the beginning of f is in y, or the beginning of f is in E0 less y. Okay, in this first case, it's easier because I do nothing. In this first case, I have this expression and multiplied by SF. And that's it. This is where I end up. It's not changed. But by the way, this I think can be written in a nice way. Yes, of course. When h is equal to f, that's in fact the formula I want. To be honest, I don't have to rewrite all of this. That formula is already good enough. This is what I want to obtain. All right. So I don't know why it's computing it. You can just stop right there. And in the case where SF is in E0 less y, well, then this is just SF times all of this, but SF times F is F, so nothing changes, so you have the equality, it's checked. So this case is checked. But now what happens when SF is in y? We have to see what psi inverse does to it. Well, then you have this vertex minus Q at this vertex. Okay, so I get what I want, but I also multiply it by. I have to see that this part vanishes. I have Q T. Is it Q? No, QSF, sorry. Yes, QSF, not QTF. I have QSF times F times TF minus QTF. Now, why it should be 0? Definitely want it to vanish. Now to use some lemma. I keep on forgetting from which side I have a 0. I have to double check. Maybe this vanishes by one of these previous lemmas. Okay, so when you multiply Q by an edge on the right, you vanish. And that's it. So this is 0. This is in full generality. This is one of our lemmas. Whatever, we don't have to bother loop, not the loop. We checked it. That if you have an edge on the right and Q with whatever vertex on the left, this is just 0. Okay. Oof. So we are good, right? So here in the second case, I have to write SF minus QSF. SF gives me what I want, but I have also this annoying term, QSF times all this mess. But this is 0 by this lemma which we proved earlier, okay? So this calculation is trivial or easy because we already proved certain lemma before, otherwise it will be quite lengthy. Okay, so now the last case, when I have E in F prime. Okay, so let me erase it. And now we have E. And I bet that as before, we will have to consider two cases, namely where E begins. Yeah, and also this probably will be nicer to write E prime, because we will probably need to deprime it at a certain moment. So let's see E prime. Okay, yes, prime, S prime. But we know by construction of a graph EX that this is S of E. Okay. So when we have E prime and we apply psi inverse, yeah, that's this fourth formula. So I deprime it and write E times QT. So E times QT. So this is this part, yeah, psi inverse of chi h. Okay, and now again we have two cases, depending on where E prime begins, which is the same depending on where E begins. And if E begins beyond Y, then nothing happens. Psi inverse is just identity. And this will be just S of E. Okay, and when I write, so the first case, it will be this times S of E. And of course, this is absorbed, and this is E QTE, and this is precisely psi inverse applied to chi E. So this psi doesn't score anything. Now, what happens in the other case when E begins in Y? Okay, then for an element in Y, we have slightly more complicated formula. Namely, we have to take SE minus QSE. Okay. So when I put SE, I get what I want, but I have to see that when I put QSE here, it will vanish. But it will vanish precisely because I have this E standing. Okay, so this part is 0. So we are good in both cases. All right, so that's it. I consider all conditions verified because everything else is really, really analogous. And I'll am bored by doing this. Now we have only 1 minute left, but I have the following proposal, namely, let's continue the lecture after the break, because I really, really don't want to go back to this proof. And we have still one more calculation to do, and this is the calculation proving that psi and psi inverse are really mutually inverse maps, all right? This means verifying 15 cases, but many of these cases are totally trivial. Some cases are easy, and it's kind of really fun. I was surprised when I was calculating it at night. Notably, there is out of these 15 cases which you have to verify. And why is it 15? Because to verify psi inverse, you have 9 cases, and to verify psi inverse psi, you have 6 cases. 9 plus 6 is 15. Only one of these cases gives you a nice, lengthy, but nice calculation. And somehow everything that you do in this calculation implies everything else. Everything else is just a repetition of some part of this calculation. So I will definitely want to do it after the break. So sorry for this last minute change, but I'm really fed up with this proof. I cannot have one proof in 3 lectures. I will just pause the recording, and instead of stopping it, and we will resume the lecture and the recording after the break. with verification that psi inverse is identity and psi inverse psi is identity. And as I said, here we'll have 9 cases, and here we'll have 6 cases. Okay, so we have this most interesting case computed all the way with all the details, and then some of these other 14 cases, we will check, and this will be the end of the story. But let me do it, or maybe we skip the break. Yeah, that will be simpler. If you can, yeah, okay. And then we'll truncate, of course, the recitation class accordingly and recover it in a week. Yeah, okay, sorry. I think I need like at most half an hour more to finish it. So yeah, let's have a break after we are done with this. I think this will be more logical. Okay, so now let's do this calculation. Now I also need the formula for psi. I have the formula for psi inverse, but now to make these calculations possible, I have to recall the formula for psi. So psi of a class of chi p. And here I have 6 cases. I have chi p plus chi p prime for p in y. I have just chi p for p not in y. I have again chi p plus chi p prime for p in f prime. Sorry, wait a second. Yeah, for p in f, not in f. For p, no, there's no f. For p in f, we are at e, not x. And just the class of chi p for p not in f. Now let's start a lot. So we have chi e star plus chi e prime star for p equal to e star and e in f, and just chi e star for p equal to e star but p not in f. Okay, so this is our reference board, and now we rock and roll with this interesting calculation. Okay, so and this interesting calculation is as follows. I'm computing psi composed with psi inverse. Apply to the class of chi p. Okay, but now we compute it for p. So this is our assumption. For p being equal to v prime the chalk is much easier to use. with V in Y. So if you want, we're taking the first case when P is in Y prime, okay? And this is a surprisingly long calculation. But let's do it. Well, when you just apply psi inverse, we remember when P is in Y prime, then what you are doing, you are depriming your P, so D prime becomes V, and then take Q, okay? So this is equal to psi of QV. So far so good, it looks so short. Why am I complaining? But then we really have to use the definition of QV and compute it step by step. So the first step is of course easy because psi of the class of IV. And now I have the sum, okay? So it's minus the sum. And now remember, we are in the domain of psi. The domain of psi is this relative concave algebra. So this is, we have a graph C, okay? So I take the preimage of V under SE. E star, where E runs the just mentioned preimage. And well, of course, I forgot, you should of course apply sine to this. Okay. Now the first step is easy because we know where V is, all right? And since V is in Y, psi just doubles it, right? Remember the formula I just wrote. So this will be chi V plus chi V prime. Okay. And now the point is that it gets complicated with the sum, because we have to split the sum into two disjoint, we have to split the set over which we sum into two complementary and disjoint subsets. Of course, I split it into the F part and not in F part, because then I have different formulas for psi, okay? So I write minus sum, and now I'll have E running the preimage of V under SE, but with F taken out. And well, then I am applying this formula for psi, where E is an edge which is not in F. Then remember that this psi does nothing to it. Okay, so I can just write chi E. E star. And of course, it's understood. This is the use of notation I already told you about. This square bracket is different from that square bracket. That's the equivalence class in the con path algebra, and this is in the Levy path algebra. Okay, so that's a different story. And now I should be yes, I should be a little bit more careful, because now, in fact, I should view my edges as edges in EX, okay? So maybe let me rewrite it, rewrite this set in the following way. I take the preimage under the EX, but I don't allow of prime, okay? So I say that I intersect it. I intersect it with E0 less Y. Okay, then this is the same thing. Subtracting from S E inverse V, subtracting F is the same as taking S E X inverse V and intersecting with E0 minus Y. So here simply I exclude Y prime, although that's redundant anyway because Y prime has things, but let's just formally speaking, this looks much better. Okay, that's what we want. And now we have to look at the other part where E is in fact in F. And when E is in F, well, our formula is more complicated. That's why I called it here. Okay, I just doubled. So let me write it down as minus the sum, and now maybe I will call it F, and well, it will run the intersection of a preimage under SEX of V with F. Yeah. I mean, I don't have to do much about nothing because indeed the preimage of SEX is the same as the preimage of SE, simply because Y prime has 6. Okay, so here we can just forget it. It's very easy. I can just without an effort replace SE by SEX. Okay, but now remember I have this complicated formula. And this complicated formula is the following. I have chi E plus chi E prime times, and the same thing for stars. This is analogous, right? So I have chi star plus I E prime star. Okay. So that's what we have to compute. And of course, what we hope is that this guy remains and these guys cancel out. And this is what's going to happen. But we need another board. Okay, so let me use the fact that addition is abelian. So I'll now write it as the class of chi D prime plus the class of chi D. And here I have these two sums. Well, the first sum is easy. I can just rewrite it. Running the preimage of SEX under SEX of V intersected with E0 less Y, and here nothing happens, so I have just the class of chi E times the class of chi E star. Okay, so that's the first part. Yeah, I just rewrote it. So now let me multiply things out and see what happens. But this is a calculation which we already did. Okay, of course we'll have two regular terms, chi E and chi E star will meet nicely, chi E prime and chi E prime star will meet nicely. So we only have to worry about expressions of the sort chi of the sort E, let me skip the chi in the equivalence class. So we look at E prime star, and we look at E prime E star. But you see, this is bound to be 0 because the beginning of E prime star is the end of E prime. But the end of E prime is TE prime, and the end of V is TE. These two vertices multiply to 0. And likewise here, the end of the prime is just the end of E prime. But the beginning of the star is the end of E. So here we have TE prime times TE. And again, this must be 0. Okay, so the cross terms vanish, and we simply have the same sum twice, but once taken with primes and once taken without primes. Okay, so let me. And I see that, of course, I was not consistent, so maybe I'll go back to writing E. That's just a dummy variable. It's only a matter of taste. How you do it in order not to confuse the things. Okay. All right. So I'll just keep the cross term and write the result. So now actually I can write just one extra sum because E will run as EX inverse the intersected with F. And here we will have chi E star plus. But no, actually, let me write it down as two separate sums, because as you can guess, I'm going to play a certain trick. So here I just repeat it, but then I will modify it. So here I will simply rewrite it. But now, here what I sum applies with primes. So chi E prime, chi E prime star. But you see, now I can wait a second. Yes, okay. Yes, that's all right. Yes. Okay. So when you look at your vertex V, okay, and it can emit edges that end in Y or beyond Y. Okay, so let's draw a picture. This is my vertex V. And what vertices does it emit in graph EX? Okay, in the graph E, it emits some edges which end in Y, and it might emit some edges which end beyond Y. Okay. So this is what happens in E, but in EX, all edges that end in Y are doubled, because here we have a disjoint part which is Y prime, and every edge which ends in Y also ends in Y prime. So when you're looking at the pre-image of V under SEX, you have to take, yes, I was talking a little bit of nonsense before, that we can just so easily replace SEN with SEX. No, this is precisely what we have to do carefully, okay? Here we could do it because we all the time had E0, right? So here we could do it. But now, if you look at the first two sums, well, first I have edges emitted at V and ending beyond Y and beyond Y prime. Then I have edges emitted at D and ending at Y, all right? So what remains are precisely the edges which end in Y prime, but this is exactly the copy of edges which ends in Y prime. So I can now change this summation. This is the same that I'm simply summing over all E prime that are in the preimage of SEX, of this preimage of D under SEX, but now intersected with F prime, okay? These two things are tantamount. That's the same summation. And now when you look, I'm summing the same things, but now first I have all edges which end beyond Y and beyond Y prime, all edges which end in Y, and all edges which end in Y prime. So this means I'm done. I'm talking all edges, okay? So let me take this picture outside. So I will simply erase this. Okay. And now I can write it down. As of course, chi v prime plus chi v, but minus the sum over E running the entire preimage of D under SEX, chi E star. But remember, we are in the Levy algebra, okay? So the Conspicuous relation is enforced at every regular vertex, okay? So this means that this part is zero. This cancels out. So this is the class of QE prime, which is what we started from. You see, we are computing psi inverse of chi p, where p is d prime. So this was psi inverse of chi d prime, and it is chi d prime. So it is identity, as it should be. Okay. Any questions here? Most important is this picture. This picture really explains a lot. It explains what happens. And the calculation is a bit subtle because you have to bear in mind that the preimage under SEX is different from the preimage under E. Under SE, okay? Because then you forget about this double part. And this comes up here in the formula, so everything beautifully checks out. Any questions? No, I don't see any questions, so let us verify, absolutely not all, don't worry, I'm not going to check 15 cases. Let's see what else is interesting in verifying psi inverse, because this will be now much faster. But I still don't want to completely skip it. Okay, let's first go back to psi inverse. Now, of course, it makes no sense to check these two cases because this is basically where you would apply identities. Right, so when P is in E0 less Y, or when P is in E1 less F, forget it. There's nothing to compute. So these cases are trivial. Also, the moment you do the unstarred part, the starred part follows. So the last three, forget it. So we did the first one, okay? And we just excluded 1, 2, 3, 4, 5. So it looks like I would like to check 3 more cases, okay? But it's going to be fast, I promise. So let's take P in Y. So I have to apply psi. I have to apply psi to P minus PP. P is in Y, okay? So we double. So psi of P will be P plus P prime. And okay, we have to see what happens over there. Remember that I just have to write it down. So this is minus psi of P, but this is minus psi of P. Yeah, actually, yes, this is a bit silly. I can just write it down as psi, and because here P will cancel, I just have the sum over E that I emitted at P, and here I have E star. Right, this is what at the end of the day we are computing. And okay, now we have the same difficulty as before because we don't know where these edges might end. Okay, so in case they end beyond Y, and let's see, psi, we are in the domain of psi, which is the conpath algebra, so it's graphing. Okay, so we end if we end beyond Y, then there's nothing happens. Okay, this is just, it will be E star. So I can write here like two parts. I have a sum, and here I have E, and I intersect this I intersect this preimage of P with, I subtract from it F. Okay. So then I have the V star after applying psi. And again, you should say, aha, but this is in the graph. This is in the graph EX now because we land in the Levi-Pack algebra. So okay, I write here EX, but here I write an intersection with E1 plus F. Okay. Yes. Okay, and what happens at the remaining two cases? When E is in F, well, you have again, you have this doubling, but we already computed it, right? We already argued that the cost term must vanish. So this is what I meant, that once you do the first calculation, basically the following calculations will follow, because the whole argument for vanishing the cost term is done. And basically what you have to do, you will have some E star plus some E star, and here you run the intersection with F, and here you run the intersection with F prime. Okay, just by the application of psi and vanishing of the cross terms. So this means that all in all, this will be the sum over the whole preimage of P under SEX, but this is the Levi-Pack algebra, so this ends up being equal to the end of P. And I hope that's what we want. Sorry, P, what am I saying? This is nonsense. This is just P. P is an edge. So this is good. This is what we started from. Sorry, P is a variance. No, these nonetheless, these are vertex. So this will add up to projection of this vertex. So skipping the Baroque notation is just P. All right, so we are done with this one. Yeah, this was very fast. Okay. Now, how about this one? How about P being equal to E prime? Okay, so I apply psi to E times QTE. But now E is in F, so this will be E plus E prime. It's really not so easy. Okay. And the psi of QTE, where TE is in Y. I have an impression that we, of course, computed it, but I don't remember the result. T is in Y, so we'll definitely have TE plus T prime. So that's the first part. And then I subtract, and here I have this sum. Oh. And I have some F's. Running the pre-image of the image on the T of E. F star, well, I should write psi. F psi. F star. Okay. Well, the first, let me see. So here are all guys. Okay, let's multiply out the first four terms. So this will be obviously E plus E prime. Okay. So I have E plus E prime. That stands. And now I have E plus E prime times that. But now, you see, the end of E prime is in Y prime, and nothing begins in Y prime. So E prime will definitely annihilate this part. So I look only at E. It should also be 0, but maybe for some smarter reason. Yes, this makes sense because E will end where F begins. So I multiply. So I have a sum, unless this is wait a second, maybe this is something where you can use yeah, but I don't know what psi of QT is. Sorry, I have to compute. So we have a sum of E psi F psi F star runs the pre-image of T. Now f is in the domain of psi, and psi goes from concave algebra, so this is in the graph D. Okay. All right. So again, we have to do these two cases, right? Where we either subtract f or we intersect with f. Do I really? Yeah. Okay. Okay. Maybe this will be. Because I suppose we want this to vanish. No, not quite. Something fun is happening. Let me backtrack to make sure I didn't make any mistakes. So I applying psi. So you see, it's trivial, but when you really want to do it, it's task. Okay, so this is what I'm computing. That's a penultimate calculation. P is in E prime. Okay, so I just want to end up with E prime at the end of the day. I apply psi. I know what happens here, and now I have this QTE term, well, which I have to, TE is in Y prime. Okay, so I can see the shortcuts. I just have to compute this, and this will give me TE minus the sum. When I apply psi to T, I double it because it's in Y. And then here I'm a little bit confused because F, all right, it begins in Y, but it might end in Y or outside of Y. So either you double or you don't double. So somehow what I want to see is that all that stuff here is equal to E. So E absorbs all of this, but I don't see yet why. Right, because at the end of the day, the result should be Y prime, okay? Here we have an E to cancel with that sum. So somehow the sum should be equal to E. That's what we are looking for. And I don't see why. This is equal to E. Okay, let's look at the first sum where nothing happens. So psi of f and psi of f star will be f star. So I'll have E F star and Y. E ends where F begins. So there is nothing wrong here. E ends where F begins. That's not automatically, yeah, I don't see how it is. Yes. Okay, it has to be the second Kunstkrieger relation. Yes. Yes. Okay, we are in the length of algebra. So the second Kunstkrieger relation is that in every vertex, okay, and that sum will be just equal to, wait a second, why? Oh yes, so that sum will be just equal to the end of E. Sorry. So I take this. Okay, I see. So I write E in front of the sum, okay? And basically what I argue now is that the whole mass is equal to T of E by the second concatenation. Because at the end of the day, well, you do nothing when your edges end beyond Y. If your edges end in Y, you have two things as you had before, because cross term will annihilate each other, but the non-cross term remain. So you will have all edges that do not end in Y or Y prime. You will have all edges which end in Y and all edges that end in Y prime. So in fact, you'll have all edges emitted at T of E. So by the second Kutzbach relation, which here applies by all means, okay, because TE is a regular vertex, because we assume it's to be in Y, so it's regular. The Kutzbach relation holds, that sum is finite, and lo and behold, this must be T of E, and I have E minus ETE, which is 0, and E prime remains, so we are done. Okay, E prime. One more relation. Any questions, by the way? Yeah, now I want to check this piece. But somehow, maybe I'll be able to use the fact that I know what happens for this one. Yeah. Yeah, maybe we can skip it because it's really quite analogous. I applied psi to this one. Okay. Well, not quite because I don't double. Okay, let's do it. So I applied psi to this mess. Okay, now chi P is in F, so I do double. Okay, so I have P plus P prime, and so this is doubled. Then when I look at the end of P, this is in Y, so this is doubled. And I just had this. By the way, here's a mistake. I should have written TE of P. And here this psi applies to this QTE. So okay, I cannot do it in my memory. So I will just write it out. I'm rewriting this formula only without this double notation. Yes, this is P TP minus QP. P TP minus QTP. Okay. Okay, but I think we already computed. We already computed this part, P times QP. This has been done, right? And we concluded. What were we computing before? Now this is something different. P minus QP. Yeah, well, these are vertices. Sorry. That's sorry, this is a completely different meaning. Okay, P is now an edge. P is now an edge, so maybe I'll, yeah. This is P plus P prime. That's what we get here. Here it is TP CP prime. And minus psi of QP. So, well, that's what we did before. We surely have P plus P prime and minus P plus P prime times psi of QP. But like deja vu, I have a feeling that we completed it before, but well, that's yeah, not quite because sorry. Yeah, this is Q TP. Yes. TP. Why did you correct me? Yes. Okay, I don't know how to do it, how to make a shortcut, so let's try it out. And this is QTP, all right. So minus sum and E runs a set of all edges emitted at TP. And here I have psi E psi E star. And sorry, this is not minus. Wait a second. The psi of TP is sorry. So here should be parentheses. Parentheses and psi of TP is TP plus TP prime. Minus this mess, but you can see that this cancels out. And because PP prime and TP prime is simply P plus P prime, so but with the minus sign. So this one cancels with that one. Okay. So we are just left with P plus P prime times this sum. And now let me see, psi lands in the Levitt path algebra. Yeah, so, okay, this is not, I don't see immediately the cancellations. Okay. Again, here we have all these cases because I look at the vertex TP and I look at edges which come out of TP. And they might, and we are now, they might end in Y, or they might end not in Y. And depending on this, we'll have different formula, but we already did it a million times. So at the end of the day, we'll have three summands. We'll have edges which end in E1 beyond in E0 beyond Y, which will end in Y and which will end in Y prime. So everything will happen. This will be just the full sum. And therefore, this full sum, because we're in the Levitt path algebra, will be just TP. So all this, yeah, and that's, this is all I told you is that in fact, we did this calculation before. So this is just times TP. So of course it gives P prime, and this is just P. And again, that's exactly what we want. So I consider it's done for C inverse. Now it will be much faster for psi inverse. It will be much faster for psi inverse psi, because out of these 6 cases, I immediately remove the start ones because it runs in the same way. So only 2 cases are interesting, the first and the third one. Okay, just let me check 2 cases. Okay, I want to take P in Y and I want to take P in F. Everything else is analogous or trivial. Okay, so let's maybe do the easier thing. V in Y, and I apply, I compute psi inverse of psi of V. But this is equal to psi inverse of V plus V prime. And here you see how smartly psi inverse was defined. Because when you look at V, psi inverse of V, this I already memorized, is V minus QV. But when you look at V prime, psi inverse of V prime, you prime V and you write QV. So plus QV equals V. Okay, done. Now we take E in F. And we write psi inverse. No, this is horrible. And you write psi inverse of psi in. That is in F, so we double it. So this is psi inverse E plus prime. And now we have to use this complicated formula. I have to look it up. We're looking for E and D prime. So for the 4th and the 5th line, okay? So you see, but then you add it up, okay? Then you add it up, and you have all the time. You have chi-e in front, and then you add up qte with chi-te minus qte. So you are left with chi-te. So you simply have chi-e times chi-te, which is chi-e, which is e, and we are done. So this actually now we can do in our memory just by staring at this formula. Okay, so I consider the theorem proven. You surely got the flavor of what happens. And as you could see, even in these so-called easy trivial cases, it's still not something that I was able to do in my memory. Of course, these calculations are now very short because of the first calculation we did. Yeah, so this ends up being here by the argument from over there. And this ends the proof. So remember, we have the relative compact algebra of E, and we have psi, which goes to the Levitt algebra of X. And here I have psi inverse. And we proved it by looking at both sides as universal algebras given by generators and relations. And then we defined psi and psi inverse on generators. We verified that they satisfy the relations. So this gives us well-defined homomorphisms in both ways. Okay. So we know where we have these two homomorphisms, and then it only remains to check that they're mutually inverse, which we just did. So these two algebras are isomorphic by explicitly given formulas. And I find this theorem quite remarkable because it's unexpected, and even the proof doesn't offer you any trick. If you want the trick, this idea, the notion of part in this theorem, it's claimed. I mean, somebody had to come up with this construction of X, okay? It's if you ask yourself the question, well, can I present every relative concave algebra as the Levi algebra of some other graph? Then you really have to first come up with what this graph is. Once you come up with what this graph is, yeah, I admit that cooking up these maps and computing the inverse and verifying everything is not a big deal. It's not a big deal. At best, at some places, you have a slightly more involved calculation, but that's it. There are no new ideas needed. The whole taste, if you want, of this theorem is in the construction of EX. And so that we ended some even time. Let me use this 4 more minutes to formulate the following proposition. I just emphasize how important is the construction of EX. And I would like to somehow convince you that in the right category, this construction is functorial. So let us now consider the functoriality of this construction of EF. And I'll just write this proposition, and I suggest that you prove it as an exercise. Okay, proposition. So let E and F be graphs. I want XE to be a subset of regular vertices in E. I want XF to be a subset of regular vertices in F. And I take a graph homomorphism, a graph morphism. And remember, a graph morphism is just, these are two self-theoretical maps, which map vertices to vertices and edges to edges and respect the source and the target maps, okay? So also, let's F0, F1 from E to F be a morphism of graphs such that there is just one crucial condition satisfied. You have to map Y into Y, okay? So F0 of regular vertices in E less XE must be contained in regular vertices of F less XF. Otherwise, formulas will not make sense, okay? Then the assignments. Well, I have to say what happens to adeno happens to vertices, and I take P in E naught X, and I map it to F X naught of P, and I define it to be just F naught of P. If P is in E0 and F naught of P prime if P is in Y, Well, remember y is just okay. This doesn't make sense. I wrote it. If p is in well, actually, if I have to, yes, I cannot. Yeah, that's slightly more so, because of this d prime, I think. I have to write it as v, and now for p equal to d prime, and v being in y, which means v being a regular vertex, which is not in x. So less x. And now on edges, we do it like this. We take fx1 and define it as follows. So this is just f1 of p for p in 1. And this is f1 of e prime for p being equal to e prime, and the end of e I don't understand why it's now so difficult to write. What happened? This is a prime, this is important, this is f1. Okay, for p equal to e prime, and the end of e being a regular vertex, which is not in xe. In other words, using our previous notation, this means that p is in f prime. Okay. Yes. But I want to avoid this notation because now we have two graphs, so we would have too many letters. That's why I want to restrict our attention just to EF, XE, XF. That's it. Otherwise, we get confused. Okay, so then the assignments, and I have to finish the sentence. Then the assignments define the morphism of graphs. Well, f x naught f x1. So first you have to check that they're well-defined self-vertical maps, and then to check that this is a morphism of graphs from going from ex to exe to fxf. And then you have to check this compatibility with the source and target maps in these modified X graphs. Okay, that's part of the proposition. And they define a morphism of graphs. And here's the key property to check that these are well defined on self-theoretical level. And then when they satisfy the property of being a morphism of graphs, and then it's obvious that they render the diagram, which I will draw commutative. So rendering the diagram which has at the top given morphism f0, f1, going from E to F. Here we go by the inclusion of graphs into EX, E. Here we go by the inclusion of graphs into F, XF. So I claim that this just derived induced morphisms complete the diagram. And this is what you can look at as factoriality of the construction of the X. So F0 X, F1 X. Rendering the diagram from this. So this is something that this connectivity is obvious, because if you look at the formulas which I gave you, I'm telling you that if my P is in the subgraph, then I do nothing, whether it's an edge or a vertex. Okay. So the commutativity of this diagram is obvious. I just wrote it down because having this diagram is very important, because that's exactly what manifests the factoriality of this construction. And I haven't seen it anywhere. It's obvious this proposition is an exercise, and I will not prove it in the lecture. I want one of you to prove it in the recitation class. So that you recall basically the definition of morphism. That's it, there's nothing more to it. But I think that this is an observation worth having in mind, okay? Because now what we want to do in the future is simply to explore morphisms between relative compact algebras. And morphisms which are induced by appropriate graph morphisms or path graph morphisms. Okay, we have this more general concept of morphisms of graphs, but it wouldn't work in here. So you see, when I say morphism of graphs, I just map vertices to vertices, edges to edges. But we in the previous semester we spent a lot of time explaining what happens when you have more general morphisms of graphs, where you of course still must map. Maybe not of course, but that's really a crucial condition. You still map vertices to vertices, but you map edges to paths, not necessarily to edges themselves. Okay, and I was thinking if last night, if somehow this more general definition could be here to manifest the factoriality of this construction of EX, but I quickly saw that it doesn't work. This wouldn't be something useful. Well, let me give you example why. If I have, so this is just an example. If I have one graph like this, so one edge, one vertex, and another graph, so this is my E, and another graph which is just one vertex, P. Okay. So I checked it. If you look at this more general definition of the morphism of graphs, is path graph morphisms, then it's completely all right. Of course, we map V into V. But it's completely all right to map E into V as well. So yeah, in peculiar situation, your map is injective on vertices, your map is injective on edges. You do not identify any two different edges. So many formulas that you would like to write down still hold. Say the first conspicuous relation will hold beautifully. That's all we need. It's injectivity on vertices, injectivity on edges. So it looks kind of hopeful. But the reason why is, so for instance, this kind of morphism could be used in studying the absolute, the conpath algebras. Because when there are no conspicuous relations, there are no second kind conspicuous relations involved. And for studying we know the orthogonality of projections, it's all happens on vertices. And if you just look at this configuration, E star F equals to Kroneker's delta EF, the end of E, or the end of F, whatever, then this is perfectly all right. The only thing that we need is injectivity on vertices and injectivity on edges, and this is satisfied here. Okay, I'm injective on vertices and injective on edges, but I just use this trick, or if you want, I use this possibility of mapping edges not to edges, and I mapped it to a path, but I mapped it to a very lazy path, the trivial path. I mean, there's nothing more because the graph is so trivial. And but it does satisfy. You do have amorphism. Things work quite all right. So you can have a map from the con of algebra of E to the conv algebra of F, but this is just a number field. Okay. And in fact, when you look at what it is, this will be an evaluation of E. Basically, what happens here is that this factors through the Levi algebra. You can see that it factors to the Levi algebra of the same graph E, but these are just functions of the circle. And then you realize that the morphism that you get induced here will be just evaluation at number one on the circle, right? This is the unit circle. So it has a point which is just has coordinates 1, 0. Okay, 0 imaginary, 1 real. So you can convince yourself that in fact the covariantly induced morphism by such a path morphism of graphs will be evaluation of this Levi algebra at 0.10. So it exists. It makes perfect sense. It's well defined. So why do I reject it here? All right. I reject it here because if you look at this condition, wait. Yeah, this condition. Of course, don't account for all possible versions of XE and XF, right? But in particular, nobody can stop us from taking XE to be empty and XF to be empty. So if you want this to work in some reasonable way, I mean, you must map regular vertices to regular vertices. Otherwise, all this collapses. It doesn't make sense. Of course, when you take XE to be all regulars and XF to be all regulars, F0 of the empty set is the empty set. So this condition is virtuous. But it is interesting when XE and XF are empty sets. And if you look into this example, which I just gave you, well, V is a regular vertex in E because it emits one edge, but it is not a regular vertex in F because it's a single. Okay, so you violate this condition. So you cannot see factoriality of this EX construction in this more general category where you take path morphisms of graphs. But here, with just one additional assumption, you don't need anything else. You just need this assumption, and then you can convince yourself that under this obvious natural assumption, this construction is factorial, which is important. In mathematics, it's very important in making proofs by construction. I mean, you want to prove the existence or to prove that you just want to prove that something works, and to make a certain construction. So this is always far more powerful if this construction is factorial. And this is a big question. For instance, in this famous Gelfand-Meinbach theorem, when you construct a space, complex Hausdorff space out of commutative unit or commutative sister algebra, this construction is factorial. So then you have the equivalence of categories and not just a statement about objects. And this is of fundamental importance. Okay, let's stop recording now and let's meet in half an hour for whatever time we have for recitation classes. I think it will be just half an hour. So let's have a break right now and have a half an hour recitation classes in half an hour. Okay, I stop recording and see you in half an hour. Stop share.